The fictional planet Isla is home to a wide array of organisms. However, when examining a map of species richness, it becomes immediately apparent that the majority of terrestrial life is located within a very limited area. Over 40% of land-dwelling species inhabit a mere handful of environments, here pictured in red. The two largest pockets of biodiversity that we see are the eastern and western reaches of the Great Iodronta supercolony, a massive forest located around the 15th parallel. This biome is one of the largest on Isla, and it houses an equally large portion of the species we see inhabiting the planet's surface. There are a great many species not accounted for by the Iodronta forests, however, so I'll now draw your attention to the other small pockets we see scattered between 10 and 20 degrees of latitude. These are Isla's spore forests, environments we've briefly mentioned in previous episodes. These unique ecosystems have little in common with forests in which we are familiar, with one major difference distinguishing them. Rather than being made up of countless individual organisms in constant competition for resources, a spore forest is built around the growth of a single, massive superorganism. This organism, Super-Organism platiphora, is without question the largest life form to inhabit the planet Isla. Although they're descendants of simple soil fungi, these organisms have since evolved mixotrophic lifestyles and complex growth patterns which challenge our definitions of mutualism, eusociality, and organismal individuality. Spore forests are intensely complex ecosystems, and it will take entire dedicated episodes to understand Super-Organism platiphora, their unique biology, and the complex cooperative and competitive interactions that they have with surrounding organisms. We need to establish a baseline understanding of these biomes before we can dive into these complex topics. So in this installment of the Isla project, we will become acquainted with the spore forest. We will look at the ecological stratification created by the growth of fungal trunks, define the various subregions of the ecosystem, and of course, meet some of the species which call it home. This is the Isla project. Hey, I have a quick announcement to make before we continue on with this episode. I'm going to be doing a Q&A. I'm putting together a special episode where I'll be making some announcements and updating you all on the future of this project, and I thought it would be fun to include some back and forth with the community I've cultivated thus far. If you have any questions you'd like answered, leave them below in the comments section or via any of my other social media accounts. I'll try to get as many answered as I can. That's all though. Now back to the video. I'd like to take some time to introduce a term which will become increasingly important when understanding the ecosystems of Isla. Rugosity describes the physical complexity of the terrain in a given environment. On a large scale, this can describe topological features like cliffs, hills, valleys, or ravines. On a smaller scale, it can describe geological surface features like the texture and makeup of rock or sediment. A highly rugose environment features extreme variability in both texture and elevation, featuring multifaceted surfaces and a wide range of accessible spaces. Conversely, a non-rugose environment is flat and featureless, with very little physical variability to speak of. So why is rugosity important when understanding the ecosystems of Isla? The answer lies in niche partitioning, or the divergence of species lifestyles based on patterns of resource use and competition. In environments with low rugosity, niche partitioning is lower because there are fewer features allowing for groups to differentiate themselves. With increased physical complexity, on the other hand, it is easier for organisms to specialize and diversify. Rugosity is particularly impactful on Isla thanks to its two most defining features, light and wind. Flat ground is particularly inhospitable as it provides little shelter from the air current, debris, or passing predators. The introduction of even minor terrain features, however, opens up significant opportunities. An embankment such as this breaks the wind, allowing for easier passage of fauna on the northern slope. Plants growing on this side are better exposed to light, and their morphologies don't need to be as streamlined as they would be on flat ground. On the southern-facing side, which never sees direct light exposure, kinet species can flourish without competition from phototrophic organisms. I will note that in the field of biogeography, rugosity often measures the abiotic features of the planet's surface. For the purposes of this project, though, this metric will also include biotic features, such as physical formations resulting from the long-term growth of organisms. And this brings us back to the spore forests, ecosystems with some of the highest rugosity on the planet, and thus some of the highest biodiversity as well. While the terrestrial surface itself may feature some physical variation, the structural complexity we see in the spore forest is mostly thanks to this structure: the fungal trunk, a single unit of growth within a colony of Super-Organism platyphora. Features of the trunk include the following. First, the mycorrhizae, which composes the saprophytic, heterotrophic half of the organism. The tangling filaments of the mycorrhizae vary dramatically in size and form massive subterranean networks which decompose organic matter as a source of nutrition. Next, we have the trunk, which extends anywhere from 1 to 10 meters in height and is the primary structural element. Finally, the ceiling, the spongy photosynthetic tissues which make up the interconnected canopy of the forest. The fungal ceiling can grow to be anywhere from 30 centimeters to a meter in thickness. While this trunk is pictured individually, it's important to remember that it is part of a greater whole within the fungal superorganism. In reality, these structures grow interconnected with one another, simultaneously competing while also sending a portion of their resources outward into the network. Again, Super-Organism platyphora is an extremely complex organism, and we will dive much deeper into its biology another time. The growth of fungal trunks creates intricate surface area for life to exploit. Upon the ceiling, organisms can make use of the multifaceted underside, using folds and cavities in the fungus as shelter or anchor points. In addition, growth is also common on the top, and we see all manner of epiphytes taking up residence within the light-exposed tissues of the fungal ceiling. The trunk itself also provides extra complexity to the layout of the environment. These biological pillars are extremely beneficial for aerial organisms, many of which use them as points of landing or takeoff when navigating the spore forest. Now that we've covered some background information on the physical structure of this ecosystem, let's take a small tour. The goal here will be to familiarize ourselves with the various subregions formed under the fungal ceiling, while also introducing a handful of the species which call them home. We begin in the outermost reaches of the forest, or the slope. Here, the fungal ceiling is no more than a couple meters high, and countless fungal trunks protrude from the ground. Competition amongst these individuals is great, and we see extremely high rates of decay amongst this growth. With the superorganism in a constant state of collapse and rejuvenation within this region, a significant amount of light reaches the forest floor below. This is the best lit zone of the forest, and it will only grow darker from here. Photosynthetic life grows anywhere the light touches, and often these plants play an active part in the decomposition of shorter-lived fungal trunks. Many are interiomorphs, relatives of species we've seen taking up residence in other forest environments of Isla. Flora belonging to this clade lack any kind of root structure, and instead grow within the tissues of the host species, with photosynthetic and reproductive organs protruding. Constant decomposition and recycling of organic matter keeps the soil of the forest slope soft and malleable. As a result, we see many burrowing species take up residence here. Some lay clutches of eggs beneath the surface, while others, like Auxilia phodiens, dig permanent burrows where they spend the majority of their lives. This species collects decaying fungal scaffolding from the forest floor and uses it to make a soft nest at the base of its den. Though they are often hidden underground, it's common to hear the chirping noises of Oxalia phodiens reverberate beneath the low ceiling of the forest slope. Concealed on the forest floor, a Dercostrid species lies in wait, looking to ambush passing prey. Its distothoracic appendages are covered in reflective scales. When positioned appropriately in a patch of light, they take on an iridescent appearance to lure in unsuspecting pollinators who confuse them for floral reproductive structures. Uninterested in this colorful display is Anupectini canis. Carried by hundreds of tiny legs, this species treks across the forest floor in search of a mate. A bright red reproductive flag growing from one end helps it to stand out amongst the murkier colors of its surrounding environment. Within scattered patches of light, we see new growth of Sorudistrati platyphora quickly emerge. Fungal saplings appear in the wake of a ceiling collapse and rapidly grow to fill the gap in the canopy above. These saplings fiercely compete with one another to reach the surface, and generally only the fastest growing, most optimally located individual will get the chance to mature and join with the other trunks around it. Even at this early stage of its development, the trunk is already harboring other life. Here, a quadrigozoan species perches atop the sapling, using its height to fish for aeroplankton in the air above. Just a little further into the forest, we can see Sornitocula lateralis, a major parasite of the superorganism making up the spore forest. As a larva, this creature burrows itself into a trunk and begins to gorge itself on nutrients flowing through the fungal network. As it does, its abdomen grows and begins to wrap around the trunk in which it's implanted. Adult forms of these parasites grow so large that they must protect themselves by growing a fan of defensive appendages down the length of their body. Tipped with stinging cells, these appendages ward off predators by injecting a nasty phototoxin, which renders the victim dangerously susceptible to UV radiation. Though they are temporary, the effects of this toxin can be harmful in a region where growth is so shaped by light exposure. As we approach the edge of the forest slope, we come to a small stream. Water sources like this can play an essential role in the sustained growth of the forest, as they provide the ecosystem with a reliable inflow of nutrients and energy. Here, an unfamiliar eodrontid tree grows up and into the fungal ceiling. Far above, it extends its photosynthetic plate into the sky. While species like this do compete with the forest for light, they often provide extra structural support for the canopy, so their limited presence has little detriment on the health of the forest. We have reached the next major subregion of this biome, the forest crest. Here, the space opens up, with the fungal ceiling growing anywhere from 3 to 6 meters above the ground. Occasional breaches in the canopy send light cascading down. However, it's dim enough that bioluminescence can occasionally be observed amongst certain species. This region of the forest is spacious enough for larger megafauna to navigate through. Migratory herds that pass underneath the superorganism are most commonly found within the forest crest, and as a result, we see a number of large predatory species as well. This is Sabramandibula pruinosus, one of the many creatures we see using echolocative calls to navigate and hunt. Far below, we can see the aforementioned stream descending into the ground, where it helps to support subterranean life hidden far below the forest's surface. Predatory species hide out around water features like this, hoping to pick off any smaller creatures dependent on them. All along the ground above, soft-bodied polyp-like organisms filter the air for biosnow, tiny specks of organic matter which floats all through the space beneath the canopy. Made from a mix of airborne spores, organic detritus, as well as living aeroplankton, biosnow sustains a great deal of life within this ecosystem, and it makes up the backbone of an entire aerial food web. Also found inhabiting the air beneath the canopy are larger flying species, like Pteropleca velox. This predatory diundecapod can be observed gliding from trunk to trunk, snatching up smaller prey using a pair of thin oral arms. While it is temporarily capable of active flight, the forest is confined enough that it more commonly relies on climbing to gain altitude. This is facilitated by long claws growing from the tips of its many legs, which are flattened and elongated to serve as wings. The body plan of Pteropleca velox is well adapted to its sheltered home, but it could never survive in the windswept atmosphere outside. This species is one of many we see here which are endemic to the spore forest. Such organisms are so heavily adapted to their local environment that they are unable to venture outside, and thus, their populations are confined to a very limited range. Every individual growth of Super-Organism platiphora hosts hundreds of species which can only be found under that specific superorganism. Isolated speciation has occurred within these environments over so many millions of years that some forests house entirely unique taxonomic families and even orders of life beneath their canopies. This is why it's difficult to discuss the spore forests the same way we did a biome like the sand plains. No two forests are the same, and any attempt to generalize the ecosystems beneath different superorganisms will inevitably be, to some extent, inaccurate. So to be clear, while some of these species may be found in multiple different forests, others may be unique to this example. As we head deeper into the spore forest, we start to see a plethora of bioluminescent structures hanging from the fungal ceiling. These are the flowers of interiomorph flora growing above. With far less faunal life inhabiting the outer surface of the canopy, it's more advantageous for these plants to attract pollinators below, and they do so using vibrant displays which are easily noticeable within the gloomy depths of the forest. As we have briefly touched on before, the eyes of faunal life have evolved an extreme sensitivity to point light sources, allowing for them to better notice floral growth and analyze paths through their environment. Species of the spore forest are particularly adept at picking out small lights in their surroundings. As we head deeper into the forest and it grows darker, we will see these luminescent displays become even more common. We have now reached the third and final subregion of this biome, the heart of the forest. Here, the strongest fungal trunks hold the canopy to heights of over 8 meters. Breaches in the ceiling are uncommon, and we only see significant light penetration when an individual trunk dies and gets recycled. This is the central region of any spore forest, and it is here that we see the reproductive casts of the fungal superorganism. Male structures grow on tangling stilts throughout this area, periodically releasing clouds of tiny gametes into the air. These trunks display extreme dimorphism from the other growths of the forest, as they have completely lost their autotrophic capabilities and exist solely to reproduce. While they may look very different from the other fungal growth, they are a part of the same species and a component in the same complex network making up this fungal superorganism. All the growth of Super-Organism platiphora we've seen thus far has been born from a single source, the matriarch. This is the most important structure of the superorganism, and without it, the forest would die. The matriarch, in addition to being responsible for the continued growth and reseeding of the forest, also stores the vast majority of the nutrients produced by the colony. This structure is easily the largest in the forest, reaching upwards of 15 meters in height and growing to widths of over 5 meters. The heart of the forest features the greatest diversity of bioluminescence. Microscopic and macroscopic organisms alike sport glowing displays which can serve a wide range of purposes. As was previously mentioned, flora use lights to facilitate pollination. Some grow from the forest ceiling, while others send flowers deep into subterranean caves where they may attract hypogeal creatures. Many aerial species use self-produced light for communication, and other, more cryptic organisms may emit sudden flashes of bioluminescence to scare away potential predators. With such an abundance of visual information being emitted within the darkest part of the forest, adopting bioluminescence can also be advantageous from the standpoint of blending in. Megafaunal species use luminescence as camouflage to help their large silhouettes sink into the surrounding area. Only in the presence of brighter light are their full forms revealed. Some organisms take on an important role in maintaining the health of the forest. This is the species Meganimus caeruleus, one of the largest herbivorous species on the planet. Meganimus caeruleus is what's known as a faunal steward, an organism or group of organisms inhabiting the forest heart, which over millions of years have developed a close relationship with Pseudostrati platyphora. Steward fauna have a heightened response to olfactory cues, particularly those released by the matriarch when it is attacked by mycophagic organisms. Stress pheromones released by the matriarch send steward species into a state of intense aggression, and they attack any creature which has been washed in the scent. This response helps the matriarch avoid damage, ensuring the nutrients it stores remain safe and its reproductive structures remain intact. The mechanism behind this behavior is particularly interesting. Nervous system development is altered in faunal stewards, occurring as a result of heavy prenatal exposure to matriarchal spores. During the development of an afflicted individual, we see increased neuron density within distothoracic olfactory centers, resulting in the heightened sense of smell which is characteristic to these organisms. Stewardism can occur within a wide range of species. However, the creature must be born within a close proximity of the matriarch for the phenomenon to be observed. Some species, like Porotennue candidimorpha, which solely inhabit the forest heart, see the hallmarks of stewardism occur in the majority of individuals. In other cases, there is variance within single species. Sabramandibula pruinosis is an organism which can occupy a wide range of the forest. Individuals hatched and reared closer to the matriarch display the characteristic changes in development, with increased neuron density in the olfactory bulb. Those out on the fringes of the forest are not exposed to the same volume of matriarchal spores, and so we do not see the effects of stewardship in these individuals. In return for the protection they provide, steward species are able to more easily inhabit one of the most sheltered environments on Isla, and they impact the continued survival of the forest which will harbor future generations. Stewards tend to grow larger and live longer lives than unaffected individuals, and they experience very few negative effects as a result of their association with the matriarch. We will further discuss the phenomenon of faunal stewardship when we eventually return to this biome. For now, though, that is where we will leave things. As a reminder, the goal of this episode was to familiarize ourselves with the general layout of the forest and to better understand the various niches created in and around the growth of Pseudostrati platyphora, the largest organism on Isla. I'm deliberately keeping the details of these forests a bit of a mystery, but more will be revealed when we return to this biome in the future. For now, though, I hope we can watch footage from this ecosystem with a new understanding of where we are and what we are looking at. Thank you for supporting this project and for sharing your feedback. And most importantly, thanks for watching.